So how you guys doing? A little tired, some of you? Because so See You Learn lets me see when things were submitted. So last night at about 11:30, before I went to bed, I looked and there were about 80 assignments submitted. This morning at 8 o'clock, there were about 230 assignments, so about 150 people submitted between 11:30 and 8 o'clock this morning. And then if you look at the times, the distribution of times, they're almost uniform between midnight and 8 a.m. So people submitting at 2, 3, 4, 5 o'clock in the morning. But that's not you guys, because you guys are here today. You woke up, so you must have submitted good and early. You must have been in the first 80 that I saw. So what's your feeling about that assignment? Interesting? No? Not interesting? No? Okay. Okay. So some people like it more than others. That's natural. If you didn't find it interesting and you're in the game stream, then maybe you should think about your choices, because you'll be taking a course next semester where every assignment is like that. Okay, so last class we were studying algorithms in some sense, and we had looked at a few different algorithms and tried to analyze them. And we finished last class. We were trying to implement binary search. So that's this searching in a sorted array where you start looking at the middle and decide whether to look at the first half or the second half at each stage. And we think that this is going to be efficient because we've done something like this before. So we saw, for example, when we played our guessing game, that you can guess a number between 1 and 1,000 using actually 10 guesses only if you apply this strategy. So 1,000 options, but you only need to make 10 guesses before you find it. So we'll get back to that in a second, but before that, there's a little notation that a couple of points of notation that I want to talk about. So one thing that you will see when you study algorithms, and it'll come up very soon, is a variable called n. And you always hear about things like, oh, the running time of this algorithm is some function of n, is n squared, is n cubed, is n log n, is log n. So what is this n? Well, in algorithm analysis, n always refers to the size of the problem being solved. So usually for us, that will mean, usually it's the length of some list, the input list. Okay. So we'll have another name for it. It'll be something like len of a in our code, but when we want to talk about running times and we want to do mathematical manipulations, that thing will be called n. And I'll try and remind us of that, but there you go. The other thing is this so-called big O notation, which looks like this. So you'll see a big capital letter O and some expression inside brackets. So I don't want to give you the formal definition of this because you're not quite ready for it yet. You'll get that soon enough. But I just want to give us an intuitive feeling for what it means. So when you see some expression like O of x, this means, so O of x means some constant c times x, and c is a constant that I don't feel like specifying. The only thing about c is that it's bigger than 0. Okay, so the notation O of x, you can read it like, okay, it's something times x. I don't feel like telling you what that something is. We'll just call it C, and it's at most that. Okay, so for example, if I say O of 1, that means just some constant that I don't feel like specifying. So O of 1, for example, you can use that as a stand-in for the time to add two numbers together, or the time to add four numbers together, or the time to multiply two numbers, or the time it takes to determine the length of an array. So all of these things are some constant time that really depends exactly on the implementation and the computer that you're using. Typically, those constants are measured in millionths or billionths of a second, but that's not really relevant. It's some constant. And you might see something like O of n, which just means some constant times n. And again, some constant that I don't feel like specifying. So if we go back to our implementation of binary search, so we had a sorted array A, and we wanted to know if some value x was in that array or not. So we did an implementation, and we actually tested it, and it works. So then we wanted to know, well, how fast is this implementation? And so we looked at each line of code and wrote down how fast that was, and we wrote things like constant time and proportional to length of A. Well, I want to use this new notation that I've been talking about there. So, so just we'll put a reminder here. Remember, n is defined to be the length of A. So if we're going to analyze this algorithm, then we'll define n to be the length of A. So here I said that checking if the length of A is equal to 0, if that takes constant time. So in this big O notation, how do we write that? O of 1, right? It's some constant times 1. I don't feel like telling you what that constant is. And returning false, that also takes constant time. And dividing the length by 2 and assigning that to a variable, that takes constant time. And testing if x is less than a at I, that takes constant time. Constant time. Constant time. Now, here's where we ran into a problem, is we wanted to call binary search recursively, and after we've expected this middle element, we either have to recurse on the first half of the array or the second half of the array. And so we said, well, what we'll do is we'll, in the first case, we'll take a slice that includes the everything up to the first half, the middle element, but not including the middle element, or a slice that includes everything after the middle element, and recurse on one of those two, depending on which case we're in. But that was a problem, because taking this slice takes time that's, we said, proportional to the length of A. So in our big O notation, what's the notation for that? O of n, right? So we end up copying about n over 2 elements. And so that's, 1/2 times n, and I don't know how long exactly it takes to copy an element, but it's some constant. So it's some constant times 1/2 times n, which is just some constant times n. So this slicing takes time O of n in both of these cases. And, well, we realized that, okay, that's not very good, because that's going to be slow. What are we comparing this to? Well, the benchmark, or the thing that we should be trying to do better than, is just searching through the array one element at a time. And we can certainly search through the array one element at a time in O of n time. That's that's just looking at each element. There's n elements and comparing it to x. So binary search isn't going to be really any faster than that if we take a slice that includes half the array. And it may even be worse, because not only do we take this slice that includes half the array, but then we recursively search on that slice. So it could even be slower than just searching the array one element at a time. In fact, it probably will be. Okay, so to solve this problem, we need to do something that's fairly common in when implementing solutions using recursion, and that's define a special auxiliary function that's going to handle the recursion and take some extra arguments. So I'll rewrite this function and call it bin search r, and it'll take an argument a, it'll take the argument x, and it'll take two extra arguments, which I'll call I and n. And we should specify what this thing does. We will search for x in the array that starts at position I and goes up to position I plus n, but doesn't include it. And we'll have to fix this code to deal with that. And here, our real binary search, where it just takes an array and a value, that's just going to be implemented by calling bin search r with the array a, the same value x, starting at position 0 and going up to the length of a. Okay, so initially, we call this recursive function with these extra arguments, and we tell it, hey, look, search through the whole array here, 0 all the way up to the length of a. But when we call it recursively, it won't necessarily be searching in the whole array A. It'll be searching only on some subset of it. Okay, and I would like to change this notation here. So this element in the middle of the array, we'll call it M, 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 and M. So this is the element that's, M is now the middle of the array, and I is the element that we're starting with. Okay. So I'll draw a picture of this where, we have this array A, and the general picture is that we have I, which refers to some index of that array, and that goes over here is index I plus n, which is not necessarily the end of the array, and we're interested in searching in this whole part of the array here. So what we want to know is x in here? Okay. So that's our question, and now we just want to implement binary search using this this strategy, or just on this subset of the array. So if we do that, where's the first position we should inspect to see if that thing is equal to x, or bigger than x, or less than x? Yep. Yeah. So where we should look is here at this element, and this is the element at position I plus n over 2. Halfway through this little subarray that we're searching for here. Okay. So instead of m being the length of A over 2, we'll actually take it to be n over 2. And we will look at position I plus m, so I plus 1/2 n, I plus m. So that's what we're going to look at. Now, how about this base case here, where we checked, before we were checking if the length of A is equal to 0. What should we check now? Yeah. So what we're worried about instead is not the length of A, because the length of A is never going to change. It's actually n. So if n is 0, we're searching in an empty subarray, then we're not going to find anything, including x. Okay, so now if x is less than I plus m, A at I plus m, then we want to continue our search for x in the array A for the value x, and we want to continue our search in this range here, right? X is smaller than that middle element we just peeked at, so this is where we want to continue our search, and this is I up to I plus n over 2. Okay. So what's the length of this array here, this little subarray? So how many elements are there in that little subarray? There's only 2 reasonable answers. And those are, somebody give me one of them. Yeah. Yeah. So it's like going to be n over 2 or n over 2 minus 1. In fact, it's n over 2, because we're interested in everything up to but not including this last element. So if you count these out, they'll be I plus 0, I plus 1, I plus 2, I plus 3, all the way up to I plus n over 2 minus 1, which is n over 2 elements, because we started counting at 0. Okay. So we want to start at position I, and the length of the array that we're searching is m, which is n over 2. Okay. So now we don't have this issue of slicing anymore. On the other hand, and it's not binary search that we want to call, it's this bin search R. On the other hand, we can start searching the second half of this subarray, which is here. So that would be all these elements. This thing starts at position m plus 1. So we want to start searching at position m plus 1. And how long is this thing? Not exactly n divided by 2, because we have this even odd thing to worry about, and we've also eaten this middle element. So if we start at position n plus 1, m plus 1, this is wrong. Is this really position m plus 1? This thing here? This is position I plus m. This is position I plus m plus 1. So it's easy to make indexing errors. I just made one. It's not position m plus 1. In the little subarray, it's position m plus 1, but in the whole array, it's position I plus m plus 1. Okay. So this is I plus m plus 1. This is I plus n. And so the number of elements in between ends up being n minus m minus 1. N minus m minus 1. And again, we don't have to worry about slicing. All right, so let's test this. So this thing, we want to make an array. A is range 100. So A is a sorted array, and we wanted to know if we do bin search 55. It's not bin search, it's called binary search. 55 takes 2 arguments. It's in A. Okay, so it says 55 is in that array. It says that 95 is in that array. It says that 0 is in that array. But, for example, if I try 55.2, it says false, because it's an array containing only the integers 0 through 99. 55.2 is not one of those integers, so it's not in there. Okay, so this seems to work. And we can even look at it a little bit and see exactly what it's doing. We can say, for example, let's print 2 values, and those will be I and I plus n, just so we can see where it searches each time it does this. And we'll include this A so we don't have to make it every time. So if we search for 55, we start out searching in the range 0 to 100, minus 1. Then we switch to searching 51 to 100, then 51 to 75, 51 to 63, 51 to 57, 55 to 57, 55 to 56, and that's when we eventually solve it, because m, if we have an array of length 2, well, actually, this is an array of length 1. It's only 55, not including 56. Then we divide by 2. We look at that value, and we see that it's indeed 55. And if we try that with 55.5, you get exactly the same thing happening, or almost the same thing happening, except that you end up at position 56, and you realize that that's where you end up with your empty array. Okay? Okay, so questions about how that works? So it's clear. This is the algorithm that you guys came up with in our 3rd or maybe 4th lecture in this course when we were playing the guessing game. Okay, so now back to our analysis of this new algorithm. Well, so what have we got? Everything that we said before remains valid, except we don't know about this thing here. Now we're setting up this function, and it's easy to set up. There's no calculations needed. We just call a function. But this function does some work recursively, and we need to account for that somehow. So this is a recursive call. With the new value n over 2. N prime is about equal to n over 2. And the same thing here, recursive call with new value, let's call it n prime, is equal to n over 2. Okay? That's fine. That doesn't really answer our question about how fast this is. So it turns out that recursion is somehow like magic in the sense that you just make the problem a little bit smaller, you recursively solve it, and somehow you get the answer back for free. So maybe we can try that same kind of magic to analyze this thing. So let's just say So let's just define T of n is equal to the running time of bin search R, where the arguments, that last argument is equal to n. It's just a definition, we'll define it. This is what we want to know. How long does it take to run bin search R on when that last argument, which is the length of the subarray that we're searching, when that's equal to n. Now that we have that definition, we can start writing down the running time. Say T of n. Let's look at it. So if I want to solve this problem of size n, well, I have to do O of 1 work here, 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 and O of 1 work here. So this is something like O of 1 plus O of 1, 2, 3, 4. So let's format this as nicely as we can. So this is something that I do when I'm having difficulty solving a problem. I spend a lot of time just formatting it nicely and hoping that the answer will pop into my head. Okay, so there's all these O of 1s. And then we make a recursive call either here or here. So that's a recursive call where the new value of n is the old value of n over 2. So how long does that take? What's that? No, I don't want to. I don't know that it's O of n or O of anything just yet. But so we want to use this recursive idea of if the thing is smaller, we somehow magically know the solution. So do we have a way of writing down the running time of bin search R when this value is n over 2? What's that called? Well, that's just called T of n over 2, right? T of n is the running time when this argument is n, so T of n over 2 is the running time when this argument is n over 2. So there you go. We've analyzed it and said, look, T of n, the running time is this bunch of O of 1s plus T of n over 2. Not really a satisfactory solution because it's kind of a recursive definition, but maybe we can work with it anyway. So the first thing I'd like to do is show you the standard trick, which is anytime you have a whole bunch of big O things and you're adding them together, you get to just keep the biggest one. And in this case, they're all the same, so we only need to keep one of them. So why is that? Well, each one of these stands for some constant that I don't feel like telling you. This is another constant that I don't feel like telling you. This is another constant that I don't feel like telling you. So 5 of those constants. And if I add up 5 of those constants, what I get is another bigger constant that I still don't feel like telling you. And so all of those O of 1s, they just become a single O of 1 here. So now what we've got is this equation that says T of n is equal to O of 1 plus T of n over 2. So now we can expand this a little bit further. T of n is O of 1 plus, we can expand this part here, T of n over 2, because we know the definition of T of n. It's O of 1 plus T of n, so that means that this thing is O of 1 plus T of n over 4. Is that clear? So you just apply this definition, but you change the argument to be, instead of n, to be n over 2, right? And when that happens, you get an equation that looks like this. You divide this by 2, and you divide this by 2, which gives you n over 4. And so, and now you plug in, here's your T of n over 2. Here's this equation that has a T of n over 2 in it. Plug it in, and you get this. Okay. Well, now we can do this trick again. So what's t of n over 4? Well, it's O of 1 plus t of n over 8. And what's t of n over 8? So when I don't get answers, it either means it's completely trivial or you're completely lost. And I suspect that both of these things are happening in this room right now. Yep. Okay, so t of n over 8 is just O of 1 plus t of n over 16. Okay. Yep.
Why are you doing this if you're basically getting the same thing, but it's just kind of writing another way? What's the point of it?
Well, how long does this go on for? I mean, does this just go on forever? Looks like I'm just going to get a whole infinite sequence of O of 1s here. Yep.
Your t of n solution, shouldn't that be t of n over 4, t of n over 8, t of n over 16?
Where? Which one? This thing?
You did that t of n 4.
This one, yeah.
Stop changing solution. T equals.
Yeah.
Shouldn't that be t of n divided by something?
I don't get it. So t of n over 4. This one here?
You got t of n over 2?
This one. I'm confused. This one.
See,
So
the solution of the constant.
tell me when I'm on the right line. The line that you're confused
Right
about.
there.
Right there.
Should be t of n.
Right. That's just what we get when we expand that line above it. T of n over 2 is a constant plus t of n over 4. This line here was just showing the work that we do to do that, which is we just apply this definition here, but we change the argument to be n over 2 instead of n. Okay. Does that clear it up? I'm confused. Okay, so do we have any problems with this list of equations? No? Okay, good. Okay, so, you know, we know the formula now, or we know the trick. We'll just keep expanding this thing. Next one is going to be, give us a t of n over 32. And now that looks like, well, this is going to go on forever, right? So that says that the running time is infinite. But we know that that's not true because we've run it and it didn't run forever. So when does this stop? Yep.
When it becomes t of n over n.
Yeah. So eventually, right, this is a recursive algorithm that has a base case, and that base case is when n equals 0, in which case we just return. Okay? So we look at this a little more closely. The real definition is this: t of n is O of 1 plus t of n over 2 if n is bigger than 0, but t of n is just equal to O of 1 if n equals 0. If n equals 0, we just return. So we don't recurse on a problem of size 1/2, and then a problem of size 1/4, and then an array of size 1/8. We stop at that point. Okay. So actually, the truth is that if n is less than or equal to 1, then we basically stop at the next round, because the next round solves the problem. Okay, so this thing finishes eventually when this number gets so small that it's less than or equal to 1. Okay. So what we're really doing here is we're taking the number n and we're dividing it by 2 and dividing it by 2 and dividing it by 2 repeatedly until it's less than or equal to 1. How many times can we do that? No, we can subtract 1 from n, and the number of times we could subtract 1 from n until it becomes less than or equal to 1 will be something like n. But dividing by 2, what sort of function have you guys seen that does that? Yeah. What's that? Yeah. So one way to almost define and certainly to think about the logarithm function, the base 2 logarithm, is the base 2 logarithm of x is the number of times I can divide x by 2 before it becomes smaller than or equal to 1. And so the base 2 logarithm of n is the number of times I can divide n by 2 before it becomes smaller than or equal to 1. So if you just keep applying this, so we'll put in some dot dot dots, what you get is log of n times O of 1. And so this is saying that this is log of n times some constant that I don't want to tell you, which means that this is some constant that I don't want to tell you times log of n, which means that it's O of log of n. Okay. So the running time of this thing, this function, is O of log n. Now, I think it's worth knowing what log n looks like for some values of n. So is it sort of like n? Is it like close to n over 2, or is it bigger or much smaller than that? So let's just do an experiment and say for I in range, let's go up to 12. What we'll do is we'll print a couple of numbers. And percentage. So we'll try for different values of n. We'll look at log of n, and we're interested in log base 2 of n. So we'll round that, convert that to an int, and we'll call that thing log n. And we'll print those two values, just to see how the two things grow in relation to each other. So what I want to print is n and log n. And let's go 6. Okay. Okay, so here's a little table showing different values of n versus log of n. So when n equals 1, log of n is 0, log base 2 of n. When n is 10, log of n is 4. So it's kind of like, oh look, it's kind of like 1/2 n. But when n is 100, log of n is only 7. And when n is 1,000, log of n is 10. So remember the guessing game on 1,000 numbers, we could solve it using 10 guesses. That's why, because log base 2 of 1,000 is only 10. And even when we get up to here, n is 1,000,000, log of n is only 20. So this tells us that we can actually search through an array or a list containing 1,000,000 numbers, and we only have to look at 20 of them to find the element we're looking for, if it's a sorted list. 10 million numbers, we only have to look at 24 of them. 100 million numbers, we only have to look at 27. 1 billion numbers, we only have to look at 30 of them. So log of n is a lot faster than searching through the array. Right? I mean, 1 billion, it's the difference between looking at 1 billion different numbers and looking at 30 different numbers. So, so it's well worth it, and it's much, much faster to do it this way. Okay, so questions about that? It's clear how binary search works, and it's clear why it runs in log n time. Intuitively, it's just because it decreases the size of the array by a factor of 2 every single time it does something, and that almost means by definition that it takes log n steps to find what it's looking for. Okay. So now we've seen that it is useful to have a sorted array versus an unsorted array because, because we can search it a lot faster if it's sorted. So now the question is, how do we get sorted arrays? So how do we sort arrays? Well, I think it's worthwhile looking at how we can do that. So let's take some array. A is range 100. So there's an array that's not sorted. And so how do we make it sorted? So there's a few ways. One, we can say sorted of A. That gives us a new array which contains all the same elements but is sorted, doesn't change A. Or we can say A.sort, which actually sorts the elements inside of A. So that's nice. That's how we sort an array. But then the question really should be, well, how does A.sort work, or how does sorted of A work? So it's not how do we sort an array. We can call a function in Python, but as computer scientists, what you really want to know is how does Python sort an array? So let's take a crack at making our own sorting algorithm. So we have an array A, and we'll either sort it or we'll return a sorted version of A, whatever is more convenient for us. Maybe we'll just sort it so that the elements of A actually get moved around. And let's look at sort of a most basic thing we can do is we can look at two elements of A that are side by side, A at I and A at I plus 1. And we can ask if A at I is bigger than A at I plus 1. So if we're trying to sort A, and we see something like this, you have A at I here, and that's bigger than the thing that comes right after it in the array. Then what's the natural thing to do if we're trying to sort A? Yeah?
You switch them.
Yeah, we'd like to swap them. So Python has a very nice way of doing that. Unlike other languages, you can just do that in one line. So that means they were in the wrong order before, And now we swap them, now they're in the right order. Okay? And we might like to do this for every I in the range 0 up to the length of A minus 1. And we only want to go up to the length of A minus 1 because we're going to look at I plus 1, and we don't want that to be bigger than the length of A minus 1. So there's some code. Let's say forgot a semicolon. Okay, so here we have this array A. It's not in sorted order. And if I call sort 1 of A, is it going to be sorted? No. So let's call it and see. So it changed a little bit, but it's still not in sorted order. Is there anything special about it? Yeah.
It only goes through it once, so it won't sort it as it only looks at one for each pair. So if we have like a line at the very end, it won't know to bring it all the way to the beginning because
Yeah. So it's only going off in this direction from left to right. So for example, 3 here is very far from its correct location. It should be over here as the 4th element in the array. And yeah, so at some point, some number and 3 get compared and they get swapped, but 3 just moves a little bit closer to where it should be. It doesn't get all the way there. Is there any number that actually gets to where it should be? Well, 0 made it, but that was by accident because it was already very close to where it should have been. Is there any number that's in the right place? 14. Was that an accident? 14 started out all the way over here, and then it ended up at the end. And we can actually look at how that happened if we print A at each step of this thing. So we start by comparing 5 and 9, and they're in the right order. Then we compare 9 and 3. They're in the wrong order, so they were swapped. Then we compare 9 and 6. They're in the wrong order, so they get swapped. Then it's 9 and 1. They get swapped. Then 9 and 7. They get swapped. 9 and 12. They're in the right order. And now it's 12 and 4. And then 12 and 14. They're in the 12 and 4, 12 and 14, they're in the right order. And now we pick up this element 14 that's bigger than everything else in the array. So at this point onwards, we're constantly going to compare 14 to the thing that comes next. 14 is going to be bigger, so we're going to swap it. And then we're going to move to a situation where we're looking at 14 again. Right? 14 is bigger than 13, we swap the 2, now we're looking at 14 and 0. 14 is bigger than 0, we swap the 2, now we're looking at 14 and 11. Then 14 and 8, then 14 and 10, and finally it reaches the end. So one thing we can be sure about when we call this routine, this sort 1 routine, is that it takes the biggest element and puts it at the end. Now what if I call it again? It'll get more sorted, and what in particular is going to be in the right place? Second highest element. That'll put 13 in the right place. And if I call it again, the 3rd highest element. And if I call it again, the 4th highest element. And now at each step, there's another number that's going in the right place until the whole thing is sorted. Okay. So actually that says each time we go through this loop, we get the next number, we get another number that's in the right place in sorted order. So if we have only length of A numbers, we can call this length of A times and we'll be done. So let's just say for range length of A. I don't want to print it after each swap, but it might be useful to print it after each iteration. So there's the execution of this thing, starting with the unsorted array, and then after one iteration, 14 is in the right place, and then 13 is in the right place, and then 12, 11, 10, 9, 8, 7, 6, and so on. Okay. So there's our first sorting routine, and this thing is called bubble sort. So this is an algorithm that has a name. It's called bubble sort. And it's called bubble sort because at each stage the biggest number kind of bubbles up to the top of the array, or the end of the array, floats its way up. So now we'd like to know is if this is an efficient algorithm. So let's analyze it. We'll start at the inside here. Swapping two elements. How long does that take? Constant time. And the notation for that is O of 1. We'll get rid of the print statements because they are not good. They're not going to help efficiency. Testing if A at I is bigger than A at I plus 1. Nothing special there. That's constant time. But here's a loop. So this thing iterates n minus 1 times, which means that everything inside the loop actually executes n minus 1 times also. Takes O of 1, but executes n minus 1 times. And the same thing here. Now out here, this thing also executes, iterates n times. So that means this inner loop here must get executed n times. And each time it executes, it does n minus 1 iterations. And so these guys in here, which execute n minus 1 times for each inner loop, also that executes n times, well that happens n times. So these things execute n times n minus 1 times. Okay. So bubble sort's actually pretty easy to analyze. Somehow the worst part of it is this stuff here, which is O of 1 times n minus 1. So O of 1 times n minus 1. And that's O of 1 times n squared minus O of 1 times n. N times n minus 1 is n squared minus n. So that's what this thing is. Now, this O notation likes to absorb things because all it really represents is some hidden constant. So we can hide the constant by just saying this is the same constant by saying this is O of n squared and this is O of n. And now when you have sums of things that are big O notation, that are big O's, the rule is you keep the biggest one. It's only the biggest one that matters. So what's bigger, n squared or n? N squared is bigger. So it's really the thing that matters. So the running time, we can summarize it succinctly as O of n squared. So now we can see what that means in real time. So if A has length 1,000 and I run bubble sort, well, roughly how many times are things going to execute then? If the running time is n squared and n is 1,000, what's that? Yeah, 1,000 times 1,000, that's a number that's a 1 with 6 zeros after it, so that's 1,000,000. No, I think it was still called sort 1. Yeah, the print statement is still there. Let's go reload everything. 1,000. So there's our unsorted array A, and if we call bubble sort, it executes pretty quickly. But it's doing about 1,000,000 operations. What if I up the ante a little bit and go to 10,000? How long is it going to take me to sort then? Or how much longer? So it takes, for 1,000 elements, it takes maybe half a second. So for 10,000 elements, how much longer do you think it's going to take?
5 seconds.
About 5 seconds? Because it's 10 times as long? So is it going to be 10 times as long? It's actually 100 times as long, because it's 10,000 times 10,000, which is a 1 with 8 zeros after it. So it's actually 100 times 1,000,000. So it's going to take about 100 half seconds. So it's looking like it's more like going to take somewhere between 30 seconds and a minute, maybe, depending exactly on how long that first one was. Okay. And it's helpful then to go back and look at this table we've been building and extend it to see how n squared fits into this picture. So bubble sort finished after, I don't know, whatever it took, 30 seconds. If I were to up this to 100,000, bubble sort wouldn't finish before the end of class, so we won't do that. But let's print this table again. So now, here's this table, but it also doesn't just show log n, it shows n squared. And you see, when n is 1,000, n squared is 1,000,000. When n is 10,000, n squared is 100,000,000. And when n is 100,000, n squared is 1,000, million, billion, 100 billion. So to sort 100,000 elements, bubble sort is going to do about 100 billion comparisons. 100,000 is a very reasonable number for a computer to do. 100 billion is getting up there. So it's not going to run in a second or two at 100 billion. Even on the fastest computers, they can only execute about 1 billion instructions per second. So it would take 100 seconds in the best possible case. But actually, using Python and an old machine like this, we'll be waiting hours for it to finish. Okay. So the short version is log n is good, fast, n squared is really bad. So bubble sort, easy to understand, but not so efficient. So let's try another version of this that's maybe more efficient. And it's a function called merge sort. So the idea behind merge sort is that it's a recursive algorithm, and I can tell it to you in words, and then the code writes itself. Merge sort is you sort the first half of the array, then you sort the second half of the array, and then you merge the two halves into one sorted array. Okay? So sort the first half of the array, we can write that as merge sort A up to, let's say, m is equal to the length of A divided by 2. So that's the first half of the array. That sorts the second half of the array. So now we have these two half arrays that are sorted. And then we call merge to merge A0 and A1 and store the result back into this original array A. Okay. Super simple algorithm, but one thing we've left out is how we merge these two things. So the picture in your head now is, I want to sort all the people in this room alphabetically by name, and I take half of you and I send you off and I say, okay, come out, I'll send you into a room, and walk out of that room in sorted order, sorted alphabetically by name, so that you come out in a nice line already in sorted order. That thing is called A0. Those are the first half the people in this room in sorted order. The other people I send to another room, tell them to do the same thing, and they walk out of that room in sorted order. So now I have these two lines of people who are standing there sorted in increasing order of names or height or whatever I choose to sort them by. And now I want to get all of them sorted together in the correct sorted order. So the first thing I need to do is figure out, well, what the first one in sorted order is. So where would I find that first one? So let's say I'm sorted by height, so that would be the shortest person in the whole room. So they come out of one room sorted by height, they come out of the other room sorted by height. Where can I find the shortest person? It'll be one of the two that's standing at the front of both lines, right? So the first line has its shortest person in the front, the second line has its shortest person in the front, and so really all you have to do is pick the shorter of those two things. Okay? So we're going to do something like, for I in range length of A, we're repeatedly going to take the smallest value from these two things. And we'll have something like some index into the first one and some index into the second one, and we'll start with the first one. And something like if A0 at I0, so the next person in the first line, if that's less than A1 at I1, then what we want to do is say A at I equals A0 at I0. And I0 plus equals 1. Okay. So this is a case where in line 0, the first person is the shorter of the two. So we take that person out of line 0, we put them in the whole line, and then we say, okay, now we move on to the next person in line 0. Well, otherwise, so the guy in line 0 is not smaller, so we'll take from line 1. So is that going to work? Might seem like it, but the problem is eventually one of the lines empties out first, and then you're trying to compare somebody in the first line with this empty line. So we have to deal, before we can safely compare the first person in the first line with the first person in the second line, we have to make sure that there's somebody in each of the lines. So, so that's something like if I0 is equal to the length of A0, then line 0 is empty. Take from line 1. Taking from line 1 looks like this.
But there should be only one piece of that at the beginning, you split it in two.
Yeah, but we don't know which one's going to empty first, so we have to be able to handle both of them. If I1 is equal to the length of A1, then we want to take from line 0. So that means line 1 is empty. Otherwise, neither of those two cases applies, so we're certain that we can actually compare the two things in each line, and then we do that. Okay. Okay, so that's merge sort. Let's see if we coded it properly. What are we missing? So we got this recursion depth exceeded error. What does that mean? We had an infinite recursion, and we should have seen that because we have this function, the first thing it does is call itself. There's no way around that. So we need some base case. And when is it easy to sort an array? Yeah. Yeah. So when the length of the array is less than or equal to 1, there's nothing to do. We just return A. Okay. Okay, so merge sort A works, and now we can test it for some larger things. 1,000. That works. Let's try 10,000. That's the one that was slow already for bubble sort. It's going to be fast or slow? Are we going to be waiting seconds for this, or is it going to be really fast? Really fast. So 10,000 took no time at all. Let's try 100,000. Took about a second to do. So bubble sort would have taken longer than we could wait for in this class, and merge sort only seems to take about a second to do this. So we'd like to understand why that is. And if we look at this code, it's really all recursion, right? So what have we got? We've got all of this stuff which takes constant time. This we don't know. This is recurse on array of size n over 2, recurse on array of size n over 2. Now this merge routine, how long does it take? Yeah, so there's this bunch of stuff here, which is just a couple of a few if statements, some simple comparisons, and a few assignments, but nothing that takes more than constant time. And the only sort of variable thing is that, well, that executes a whole bunch of times. It executes length of a times. So this thing takes length of a time, and we define length of a to be n. So this part takes O of n. Okay. So, so this we can actually write down using one of these recurrences again. If we say, let's call it m of n is equal to the running time of merge sort on the input of length n, then we get this equation that says m of n is, well, O of 1, O of 1, O of 1, O of n. What's bigger of those things, O of 1 or O of n? O of n. So we just keep that piece. And then we call merge sort on an array of length n over 2. That's here. And then we call merge sort again on an array of length n over 2. Okay. So that's the running time. Now, all right. So we've seen this trick. We can first make this as simple as possible. So m of n over 2 plus m of n over 2, easy way to write that is just 2 times m of n over 2. And now if we expand this, what happens? No. So m of n over 2, if we apply the definition, that says that this will be O of n over 2 plus 2 times m of n over 4. Right? M of n over 2 is O of n over 2 plus 2 times m of n over 4. Okay. So let's keep simplifying. So we get an O of n. So the 2's cancel here. 2 times O of n over 2, we can think of that as O of n. And then we've got 2 times n of m of n over 4, 4 times m of n over 4. You see that? This 2 multiplies everything inside the brackets here, including this 2, which gives us 4 times m of n over 4. All right, can we do this again? Let's try. M of n over 4. Well, that's going to be, what did we say? O of n over 4 plus 2 times m of n over 8. Let's simplify all that again. 4 times O of n over 4 simplifies to 4 times n over 4 is n, so this is just O of n. And this 4 and this 2 multiply, so here we get an 8 times m of n over 8. So if I do this again, what do you think is going to happen? Same thing again. We're going to get an extra O of n, and this is going to become 16 and 16. Now, how many times does this go on for? Yeah. So this stops when we call merge sort on an array whose size is 1 or 0. And so what we're really asking is how many times can we divide n by 2 before its size becomes less than or equal to 1? Well, that's log n. And so what we're going to end up with is just a whole bunch of O of n plus O of n plus O of n plus O of n log n times. So what we get is log of n times O of n, which is O of n times log of n. Good. Now, if we just add one more thing to this table, let's put it here. Percentage. Yes. So, oops. Okay, so now we can actually get some idea what this n log n running time means that we just deduced. So n log n is the running time for merge sort. What does that look like? Well, we sort of knew this already. We knew what n was and we knew what log n was. So it's just n times log n. But to give you an idea, for n is, let's say, here we are at 1,000,000. Well, n log n is 20 million. Not unreasonable for a computer to do. Whereas this n squared here, 1,000,000 and 1,000,000 times 1,000,000 is like 1,000 billion. So that's a 1 with 12 zeros behind it. This is a 2 with 7 zeros behind it. So a huge, huge difference. And that's why merge sort will even reasonably sort in a few seconds, millions, something like a million elements. It'll take 20 million instructions to do. For 10 million elements, it's taking longer, but 10 million is a lot of elements to sort. So, so there you go. Now you know merge sort, and you have some idea about these running times for various common running time functions. We'll leave it at there today.